Hamiltonian of this thing, which you don't know, but it is a Hamiltonian. If you knew it, you would know exactly what those gates were, but you would take a whole lot of them.
Correct.
So there's no descriptional complexity.
There is no descriptional complexity in this whatsoever.
How much number crunching?
Correct. Exactly right. So I'm just about to show an example that will manifest this, but I very much mean total number of gate complexity, not depth, not length, not Kolmogorov complexity, not logical depth, not any of these other notions of complexity, which are all great notions of complexity, but I can go through each one if you ask me and explain why that is not an appropriate notion of complexity to be dual to the linear growth of the wormhole. The only thing that'll work, at least out of that list, is the definition of complexity I'm about to give. So what I mean is the computational complexity of a quantum state. I'm going to give you now a sort of working definition of that. In the unlikely event I have time at the end, I will give you what I think is a better definition of, or I'll gesture at what I think is a better definition of complexity. But this is a working definition of complexity that exhibits what I want to, what we need. And it's the computational complexity of a quantum state. So the state, of course, of interest is the state that lives on the boundary. We're asking what is the property of the state that lives on the boundary. And just heuristically, the definition is, I probably don't need to tell you this, especially after what you've just heard. But the question is, are these two states near to each other or not? And what are these two states? One of these states is the entire Earth as it exists right now, the quantum state of the Earth. Let's say the Earth was in a pure state. Tensor product with a single electron spin that is up. And the other state I want you to consider is the Earth as it is right now, tensor producted with a single spin that is down. And the question is, are these two near each other, these two quantum states? And clearly, if you take the inner product metric, they are not only not near to each other, they are as far apart as any two states can possibly be. Why? Because it doesn't matter that the two Earth states are identical. They're tensor producted with two states that are orthogonal, therefore they are orthogonal. These two states are not near, according to the inner product metric, according to the inner product distance. But nevertheless, they are clearly an intuitive sense in which they are proximate. And that's the sense in which you just need to apply a single NOT gate to get from one to the other. Sort of heuristically, the definition of complexity I'm going to use is the definition in which, even though these two are as far apart as it's possible for two states to be in the inner product metric, these are nevertheless close. Okay, so let's have a slightly more rigorous definition. The definition of complexity is starting in some reference state, and I have a particular reference state in mind for the example I'm going to give. How many fundamental gates are needed in order to make the target state, in order to produce the target state? What is the total number of gates in the quantum circuit required to build the state that I'm after? And once I've specified the reference state, I've specified what the fundamental gates are. So for an example might be just give myself all 2-qubit unitaries. Clearly, if I give myself every possible gate, then I can just get to every n-qubit unitary. I can get to anywhere I like in one step, so that's not going to do. Instead, I'm going to give myself just 1 on 2-qubit gates, for example. How many of those do I need to make the target state? Possibly giving myself some epsilonic accuracy with which I need to get close to the target state in order to declare victory. Okay.
Are you basically reverse engineering this setup so you get linear?
I'm certainly choosing this rather than any of the other definitions of complexity in order to get linear. None of the other definitions of complexity would get linear except for circuit depth, and there's a reason to. Nothing I've shown you so far rules out circuit depth, but I could explain why that's bad later. Yeah.
Well, so you don't want to. These fundamental gates, maybe you want to just restrict them to a finite size alphabet rather than any possible 2-qubit gate.
Yeah,
Does that not matter very much?
I mean, it doesn't matter very much. I mean, for sake of definition, let's give myself, T gates and phase gate, T gates and C naughts and whatever you like, but just some universal finite set. But we could also play the game where you give me every possible 2-qubit unitary. It's not actually going to matter for what I'm going to say. Okay, so that's the definition, and you really don't need to see this, but I will just remind you, imagine starting in some reference state. The question is just how many of these gates do you need to build the target state to within some accuracy epsilon. Okay, that is the basic conjecture. And now I can start giving you reasons why this strange sounding conjecture might possibly be true.
What is the conjecture?
The conjecture is that the property of the quantum state that you need to calculate, which is so that we have the ADS-CFT conjecture, this gauge gravity duality, in which we have a quantum gravitational theory that is dual to a quantum theory, a non-gravitational quantum theory. And we've identified a property of the gravitational theory that we're interested in, which is the length of the wormhole. We know that that is growing linearly with time. And the conjecture is that the game is finding a property on the other side, a property of the quantum state, which is dual to the length of that wormhole. And the conjecture is that it is the computational complexity of the boundary state. So the conjecture is that complexity of boundary state equals wormhole length of bulk state.
It's not, so you don't think it's just conditional description complexity?
I do not think it is conditional description complexity, and the reason I don't think it's that is that property would grow logarithmically with time, and therefore would not match the linear growth with time that occurs for the wormhole. Yeah.
Just to get some details straight, so there is only one bulk. Sorry, there's only one boundary. So there's only one CFT on the boundary. On that CFT, you're constructing a thermal field belt.
So actually, a eternal two-sided ADS black hole has it has one boundary, but the boundary is two disconnected spheres, one on either side of the wormhole.
So this is sort of the computational complexity of the mapping between one side and the other?
It's the computational complexity of producing the state.
Oh, I see.
Yeah.
It's an entangled state.
It's an entangled state, right.
Producing the entangled state from a standard non-entangled state.
Well, you can't actually... I'm going to imagine I'm acting with local gates on either side, so I couldn't produce a entangled state from a non-entangled state.
Standard vanilla entangled state.
Exactly, yeah.
Conditional depth.
Yeah.
I'm still a little unclear about this wormhole and its
But you
relation to the
start
black
with
hole.
something simple.
It is a...
Wormhole and where's the black hole? And how are they related?
That is a gravitational question that I'm just going to quote the answer to you, which is that the wormhole lies, for these idealized eternal black holes that have been around forever and that are sort of the harmonic oscillator of quantum gravity, the wormhole lies behind the horizon of the black hole.
But it connects what?
It connects the two sides of the black hole. You're used to there only being...
Can you not make the picture so I have this black hole?
Correct.
And then inside I have like
a singularity, and there's a wormhole that goes through to in these idealized black holes that goes through to another asymptotic region on the other side of the black hole. So these black holes are not the kind of black holes that form if you take a dirty star and collapse it to form a black hole. Those are one-sided black holes. These are these sort of mathematically idealized black holes that have been around forever, discovered by Kruskal discovered by Einstein and Rosen, and then explored more fully by Kruskal in the 1950s. That if you just continue as far as you possibly can this black hole metric, you will discover that there are two sides to the black hole metric. There's one asymptotic region, and then there's another asymptotic region on the other side of the black hole through the wormhole.
Everything's inside the black hole?
Inside is a difficult notion here. You need to go through the black hole to get there, but you can't do anything, because if you can't move faster than the speed of light, you can never reach the other asymptotic region. Someone from the other asymptotic region can jump in, and you can jump in, and you can meet behind the horizon of a black hole, and then both die, because you'll hit the singularity soon thereafter. But that might be worth it, depending on how urgently you wish to meet the person from the other side. Yeah.
And it's growing with linear time forever, or just?
It grows linearly with time forever as far as the classical, semi-classical description of the black hole is concerned. The semi-classical description of the black hole probably lasts for a time that goes like e to the s over h bar.
And it has to if you believe in ACFT, I guess, because otherwise you need a number of states to describe it.
Yeah.
You'll get recurrences eventually.
You will get recurrences eventually. Yeah. Hawking page black holes. I don't want to. Yeah.
First, when you say other side, do we have, does this mean in terms of time?
Can you repeat your question?
You say other side of the black hole.
Yeah. You will never reach the other side of the black hole. So I drew this diagram to begin with that maybe was helpful or not. This is sort of not essential to what I'm saying. It's just a sort of ingredient, but it's not essential to understanding the basic claim I'm making. But since people are asking, and I did, after all, bring it up, I will explain it. So this is us, this quadrant here of this diagram. Definitely don't worry about what's going on down there. This is them, the people who live in the other asymptotic region of the black hole. And then this is the singularity.
As in other asymptotic region, it is in time or in
It's space-like separated from us, so which means in order to get there, you'd have to go faster than the speed of light.
Very far away, another place that locally looks like an ordered black hole.
Right. Yeah, this is actually, understanding this diagram is not essential to understanding the basic claim I'm trying to make. The basic claim I'm trying to make is that there is some property of the black hole, don't even worry what it is, I'm going to tell you it's called wormhole length, that is definitely, everybody agrees, classically growing linearly with time. And
So it formed at some point, and then,
this actually it's actually been around forever according to this diagram.
and then it's growing and growing and growing, but it hasn't grown forever.
It's been around forever, and the complexity of it actually was shrinking for, if you believe the bottom half of this, for a really long time, and then it minned out, and then it starts growing again. So this is the zero time slice. The reason I brought up two-sided black holes is because those are the sort of simplest example of a black hole as far as people who do relativity and quantum gravity are concerned. They're these sort of beautiful idealizations in which you haven't austere examples in which you haven't introduced anything else. Let me banish the two-sided black hole and say that you could just say exactly the same if you, at the cost of being messier, if you made a black hole just by collapsing matter down in stellar collapse, then you just have one side of a black hole. But you could still ask what is the length of the slice that goes into the black hole. That would also be growing linearly with time. So maybe at the cost of being messier, that's what I should have said to begin with, is that the same is true of a one-sided black hole, which is the kind of black hole that forms by stellar collapse. Yeah?
And why does the number of gates require change? Because I can see that if this changes by time, the length changes by time, then in the corresponding theory I would need different number of gates to create the state.
I'm going to take your question as being how does a complexity evolve with time? And so that is, in fact, the topic of the next slide. I hardly need to tell you the answer to this, which is that if you have an n-qubit state, you need 2 to the n complex numbers to specify it. And so the number of exactly orthogonal states of n qubits is 2 to the n. But the number of almost orthogonal states is not 2 to the n. It's 2 to the n, where 2 can be used advisedly here. It just means it's doubly exponential in n. The number of states that are almost orthogonal to each other in an n-qubit state are doubly exponentially large in n, and that's really what makes complexity an interesting property.
So what is almost orthogonal?
Let's say that they are, it doesn't really matter, but let's say that they are 99% orthogonal. Their inner product is less than 0.01.
And this staining doesn't depend on this epsilon?
It does. There are logarithms of epsilon living at the second level of the exponent. I'm just interested in how it scales with n. Yeah, I mean the twos you can take under advisement, but it's a I'm just trying to get at the fact that it's double exponential in n, not, for example, single exponential in n. Hilbert space is huge, whereas the number of circuits clearly grows merely exponentially in the number of gates that you might wish to lay down, which means that the maximum complexity is exponential in n, not polynomial in n. And really that, from the physics point of view, is why we are interested in this. That's a hint that complexity is an interesting quantity to consider. Because this wormhole grows linearly with time and continues to grow linearly for at least an exponential time, a time exponential in the entropy of the black hole. And in that, it's quite unlike any other property you might, so that's what we know about the bulk. And if you're asking what is the property of the boundary that could possibly correspond to that, the property of the boundary that could possibly correspond to that has to have the ability to keep growing for a really long time, for an exponential time. Most properties of the most coarse-grained properties of the boundary you might aspire to write down do not have that property. Most coarse-grained properties cease growing after the system is thermalized, or cease growing after a polynomial time. That's why we need to go to a fine-grained property of the boundary in order to correctly capture the fact that the linear growth of a wormhole keeps growing for an exponential length of time.